f such that x maps onto f of x is a periodic function defined for x an element of R. The period is as indicated in the diagram. So we want to write down the period and range of this function. Now the first thing I will do is write down the range. So the range is the y values that all our x values range over. The y values run from -1 to +1. So no matter what value of x you take, whether it's here or here, anywhere at all, the corresponding y value will be a number ranging from -1 to +1. Now, this function repeats itself at over a certain interval. For example, if we look at f of 0, f of 0 is -1. The function increases as x increases here. The function is increasing, reaches a maximum here at x equals 2. Then it decreases again from x equals 2 to x equals 4. And then the function starts to increase again. The same pattern repeats itself. The distance from this point to this point is known as the period. So we see that f of 4 is also -1. So this basic pattern here repeats itself. The period is this distance here, which you can see is 4. So the idea is this: if we take any point on the curve and increase its x value by 4, we get the same point on the curve. So these 2 points have the same y value. Of course, you might say if we increase it by 8, that will happen as well. That's true. We could say the period is 8, which is 2 times 4. But the period is always the smallest interval of x. The idea is that if we calculate f at x plus 4, we'll get the same answer if we just calculate f at x. And this number, the smallest value here that has this property is called a period. So, for example, if x is, as shown here, say this value of x is about 1.3, then we would see that f of 1.3 plus 4, which is 5.3, equals f of 1.3. So say this value here is 1.3, then we add 4 onto it. 1.3 plus 4 is 5.3. And if we calculate f of 1.3, we get the same answer as if we calculated f of 5.3. We want to find f of 71. Now we can use the fact that we have a periodic function to extrapolate the value of y when x is 71. If we look at 71 and divide it by the period, divided by this interval here, this is the range of x values for which f of the function repeats itself. So we get 17 3/4. That means we can write 71 as 4 times 17. 4 times 17 is 68, and we have 3 left over. 68 is a multiple of 4. So that means that f of 0 will be the same as f of 68. (68) is 4 times 17. So that tells us that f of 68 will actually equal f of 0. f of 68 is -1. And this pattern will repeat itself again. So as long as this number is a multiple of 4, the pattern will repeat itself. See, the pattern repeats itself at 4 here, and if we keep going, it'll repeat itself at 8, then at 12, 16, 20, 24, 28, so on, all the way up to 68. It'll repeat itself at 68. This pattern here in blue. So knowing that, if we extend this graph on, we have that f of 68 is minus 1. F of 69 will be the same as f of 1, which is 0. F of 70 will be the same as f of 2, which is 1. And f of 71 will be the same as f of 3. F of this number here. So I've written in red what the values 68, 69, 70 and 71 correspond to. They correspond to 0, 1, 2 and 3. F of 71 equals f of 3, which is 0. We have the function y equals 4x minus 1 multiplied by 3 minus 2x squared. We want to differentiate it, get dy dx. Now method 1 will involve just multiplying this out, because it's possible to multiply this out because neither of these brackets are raised to a power. So we just multiply 4x into the right hand side. So we 4x by 3 is 12x, 4x by minus 2x squared is minus 8x cubed. We have x to the 1 by x to the 2 is x cubed. Then we have minus 1 into the right hand side, so we get minus 3 plus 2x squared. And if we simplify this, we get 12x minus, well actually it is simplified. All the terms are unlike terms. Next thing we do is we just differentiate term by term. We have it written out as a series of terms. We differentiate each term. The derivative of 12x is 12. The derivative of minus 8x cubed is minus 24x squared. The derivative of minus 3 is 0. The derivative of 2x squared is plus 4x. That's method 1. Method 2 will involve using the product rule. So we have a product of functions here. We call one of the functions u and the other function v. So that y equals u times v. And the derivative dy dx is u times dv dx plus v times du dx. In other words, it's one of the functions times the derivative of the other function, plus the other function times the derivative of the first function. That's what it is essentially in words. So dy dx is the first function, which is 4x minus 1, multiplied by the derivative of the second function. So if we differentiate 3 minus 2x squared, what do we get? If we differentiate 3, we get 0. If we differentiate minus 2x squared, we get minus 4x. Then we have plus v, which is the second function, 3 minus 2x squared, times the derivative of the first function. Differentiate 4x minus 1 with respect to x. The derivative of 4x with respect to x is just 4. The derivative of minus 1 is 0. And then we multiply this out. Minus 4x by plus 4x is minus 16x squared. Minus 4x by minus 1 is plus 4x. Plus 12 minus 8x squared. So we minus 16x squared minus 8x squared. That's minus 24x squared. We have plus 4x plus 12. This thing here is the same as this thing. It's just written in a different order. Terms are ordered differently, that's all. So if neither of these expressions are raised to a power, it's probably easier just to multiply them out and differentiate term by term than it is to use the product rule. But very often one of these expressions will be raised to a power. For example, if this second expression v was raised to the power of 10, then of course it would not be possible to multiply this out. You'd first of all have to raise 3 minus 2x squared to the power of 10, which would be unfeasible of course. In that situation we'd have to use the product rule, and when we work out dv dx, when we differentiate 3 minus 2x squared to the power of 10, we'd have to use the chain rule on this. In b part 2 we have the function y equals 1 over x squared minus 3x, where x is not equal to 3. I'll just briefly mention about x not being equal to 3. Why is that thing stated? Well, if we plug 3 in for x, we're going to get 1 over 3 squared minus 3 times 3. That's going to be 1 over 9 minus 9, which is 1 over 0. This thing is not defined. I explain in other videos why this is not defined. Because if it's equal to some number, say it's equal to a, 1 divided by 0 is a, well that would mean that if we multiply a by 0 we should get 1. If we cross multiply, a times 0 should equal 1. But any number times 0 is 0. That's like saying 0 equals 1. That's obviously nonsense. So 1 divided by 0 is not any number. As a matter of fact, you could think of it as an infinitely large number. As x gets closer and closer to 3, this function here, well, first of all, the denominator gets closer and closer to 0 actually. Say we put in 2.99 for x. If we work out f of 2.99, we get a number that's 1 over some very small number here, some number that's very close to 0. And when we divide 1 by a number that's very close to 0, we get an infinitely large number. We get a very large positive or negative number, depending on whether this thing here is positive or negative. But I'll explain more about that in a minute. So x is not defined at 3. Now, we want the range of values of x for which dy dx is less than 0. Well, that basically means we have to go and get dy dx. We have to differentiate this function. And then I'll explain how we solve this inequality. And I might show a graph as well, just to link up a graph with the meaning of dy dx and where dy dx is less than 0. Okay, there's two ways we could get dy dx. We could use the quotient rule. This is a quotient, which is just a fancy word for a fraction. U is the function on top. U is just 1 in this case, and v is the function underneath, or the expression underneath, which is x squared minus 3x. So u is 1, v is x squared minus 3x. We need du dx and dv dx. To get du dx, we differentiate 1 with respect to x. This is just a constant, so the derivative of any number with respect to anything is actually 0. dv dx is 2x minus 3, and then we plug it into this quotient rule formula, and we get our answer. So here it is. We multiply v by du dx, and then subtract u times dv dx. So we have x squared minus 3x times 0 minus u, which is 1, times 2x minus 3, and then we divide it by v squared. So v is x squared minus 3x, and we have to square it in the denominator. So simplifying this, 0 times anything is 0. We have minus 1 into this, that gives us minus 2x plus 3, and the denominator we leave, we don't expand out the denominator. So that's dy dx, and we want to see where this is less than 0. For what values of x is this fraction here less than 0? Now, for a fraction to be less than 0, for a fraction to be negative, that's what less than 0 means, of course, we need that the numerator and denominator have different signs. So let's look at the numerator and denominator. Well, for different values of x, the numerator could be positive or negative. For example, if I put in x equals plus 10 here, I get minus 2 times 10, or minus 20 plus 3, which is minus 17. That's negative. But if I plug in, say, x equals minus 1, I get minus 2 by minus 1 is plus 2 plus 3 is plus 5. That's positive. So you see, that depends, but this denominator is clear cut because we have something squared. It's a very important idea. If we take anything squared, it's always positive. So the denominator is always positive. So for all x, no matter what x is, when we work out x squared minus 3x, that could be negative or positive, but when we square it, it's always positive. So if the denominator is positive for all x, and we want this fraction to be less than 0 or negative, we must have that the numerator is negative. We must have the numerator negative. So what follows is that minus 2x plus 3 must be less than 0. It can't equal 0 either, by the way, because if it was equal to 0, then we'd have the entire fraction would be 0. We don't want that. We want it to be strictly less than 0, not less than or equal to 0. So we have to solve this inequality. So we just bring plus 3 over, so we get minus 2x less than minus 3. The next step in solving the inequality is to divide both sides by minus 2. So we have minus 3 over minus 2, that's plus 3 over 2. But when we divide both sides of an inequality by a negative number, we change the direction of this sign, so the less than sign becomes a greater than sign. It's very important. That's the only way that inequalities differ from equations. when we divide both sides of an inequality by a negative number, which is what we have to do here to get x, we change the direction from less than to greater than. That makes sense. Like a very simple example would be, say with numbers, we know that 1 is less than 2. But if we change the signs, we get minus 1 is obviously greater than minus 2. So this is our answer here. For values of x greater than 3 over 2, dy dx would be less than 0. Let's see what this means graphically. It means that for values of x that are greater than 3 over 2, 3 over 2, by the way, is 1.5, dy dx is negative. That means the slopes of tangents to the graph are negative. So dy dx is the slope of a tangent to the graph. That's a very important idea. So I don't know what the function looks like. I'll show you a picture in a minute, but I do know that the function will be decreasing for values of x greater than 1.5. It'll always be decreasing. What exactly it looks like, I'm not sure. But the idea is that if we take any value of x that's greater than 3 over 2 or 1.5, get dy dx. dy dx will be the slope of this tangent. That slope will be negative. It's a line sloping downwards like this. Lines sloping in the other direction are positive. Lines going in this direction are positive, but lines going this way are negative. So if we take any value of x that's greater than 1.5, that means the graph itself is decreasing for values of x greater than 1. So you can just type in your functions 1 over x squared minus 3x and look at the graph. You can see here x is 1.5, and you can see that for values of x greater than 1.5, you can see that the function is decreasing. So this is what it looks like. So all the tangents to the function for values of x greater than 1.5 have negative slope. The tangents are like this, they're going in this direction, and this continues on. Well, it doesn't actually go vertically down. It does, you know, I think we might be approaching an asymptote here. But anyway, tangents are negative for values of x greater than 1.5. The tangents have negative slope. We can differentiate 1 over x squared minus 3x. Here's the answer. It's written in a different form from what we wrote it in, but it's the same thing. And if we can look at a graph of the derivative, and you can see that at x equals 1.5, the derivative is 0. Okay, so this y-axis now is actually dy dx. This is dy dx. So when x equals 1.5, dy dx is 0. But for values of x greater than 1.5, you can see dy dx is negative. All these points here have negative values of dy dx. This is a dy dx axis.